Good evening and welcome to the third and last session on water dowsing. Some of you may have been with us since this morning where we started at 10 a.m. giving an overview of our efforts. And some of you may have participated in the 3 p.m. session on the technology. If you were not there, you can find the presentations online on some platform that old people like me don't understand, but you'll find it. My name is Paul Toft. I work for the Grundfos Foundation, and we collaborate with Aarhus University and with Water Mission, to find suitable well sites in sub-Saharan Africa, South Asia, in the last mile communities where you won't have a decent business case. As I said, we have already given an overview, and we have discussed the hardware, the technology, and the measurements. And now it's my pleasure to give the word to Dennis Kronbacher from Aarhus University, who will tell you about the data and what we do with it.
Excellent. Thank you, Paul. Jump to the title slide. Oh, sorry, there's the frame here. So today, in this final session, we'll be talking about the data. So specifically, we'll talk about some of the data products that we're producing with this type of a Ttem system, how we can interpret them, how we can use them to better understand groundwater systems. And then finally, I'll give a few examples from some of the first campaigns that we've conducted in Tanzania, and also talk a little bit about a campaign that's being done in South Africa as well. First, a little bit of context. A little bit of context. So as hydrogeophysicists, we're generally interested in better understanding groundwater systems and groundwater processes. And so we are generally, at least in our research group, trying to build research tools or imaging tools that can better understand some of the properties at subsurface. So some of the properties that we're trying to image are things such as, is there an aquifer present in depth? And if so, how thick is this aquifer? What's its regional extent? How connected to regional systems is this thing? We're also interested in better understanding where are there barriers to flow, clay layers, where are there potentially highly fractured zones. We're also trying to quantify physical properties like water content, which gives us insights into the total water that's present at depth, or things like permeability that gives us insights into how well water can flow. All of this kind of information is really key when you're trying to build out your conceptual understanding of what the local groundwater systems may be. And then we'll go to the next slide. Because ultimately our goal is to try and produce images such as this, and to produce these kinds of images in a cost-efficient, rapid manner, and to do so in a reproducible way that a person, ideally without a significant amount of training, is able to also begin to do themselves. So this type of image is actually produced with the system that's at the core of this project, called the Ttem system. So what's happened in this particular Danish field is that we've driven this system around on the ground surface. All of these black dots that you can see at the top of the image, these correspond to data locations where we've actually driven the system and performed an experiment and produced a 1D image of the subsurface. And when you stitch all of these different soundings, or data points, I guess you would call them, together, you can build these very high resolution, complex images of these 3D systems. And so from these kinds of images, it gives you a lot of powerful insight into the connection of these systems, where they're located, and lets you steer drilling efforts to more likely attractive targets. And just as a point of reference, the alternative, if you were not to perform these kinds of imaging practices, would be to rely on more traditional hydrological mapping techniques. Things such as walking around at the ground surface, doing traditional geological mapping, where you're looking for surface expressions of these geological units, and then trying to use some previous knowledge or implicit assumptions to try and map the extent of those units underneath the subsurface. You could also use more traditional methods, such as exploratory boreholes, where you're actually drilling boreholes directly into the earth, which is both an expensive proposition, but also one that's really only giving you local information about the subsurface. And at the end of the day, even if you have, say, 10 or 15 boreholes in a particular area of interest, you're still left with quite a sparse data set, and you're forced to interpolate between each of, or all of these sparse data points. And so there's a lot of uncertainty that persists in your final conceptual model. And the unfortunate reality is that that uncertainty can propagate towards ultimately resulting in a failed well in certain cases. And so when we're working with these kinds of high resolution 3D images, one thing that's always extremely important is to try and communicate these results in a format that's digestible by a non-expert end user, at least a non-geophysicist potentially. And so one of the standard data suites that we'll deliver to an end user, next slide, is something that looks like this. So in the top left panel, we have an image that's more or less showing some kind of metadata about the survey. So in red dots, we're seeing locations where the system had actually been driven on these fields. So typically we'll deliver a series of these types of kind of metadata maps to give you some supplementary information about the survey. So in this case, it's giving you some insights into data coverage over these particular fields. And then in addition to this, it'll also be paired with what we call an example in the top right here. We're looking at a mean resistivity map. These represent slices through that 3D volume. So at times, it can be difficult to fully appreciate the complexity and these kind of lateral continuity and extent of these different geological units when you're viewing only the 3D image. So what we often do is we'll slice it. So in the top right case, it's a slice horizontally through that 3D space. So you can think of this as representing the mean resistivity values for a fixed depth beneath the surface. So an image like this is really useful in terms of quantifying the lateral extent of different units. So in the top of that part, you can see, or top of that image, you can see a dense blue area where you have a quite expansive clay that happens to be present. And in the right-hand side, you can see this dark red section that seems to have fingers or some sand channels that are cutting through at this particular depth. Another way of viewing these kinds of results is what we call a depth slice, which is what's visualized here at the bottom panel. And this corresponds to a vertical slice through that 3D profile. So it's a slice where on the vertical axis we have depth. So you're looking further into the subsurface as you go down that axis. And then it's along some line. So the X, or the horizontal axis, corresponds to lateral displacement. And in this particular image, it's actually showing you a vertical slice that corresponds to the yellow line in that upper left panel here. So what we've done is just viewed straight down into the subsurface, and it's a really useful indication of the lateral extent of these units. So one thing that you can immediately see is that you have this thick, expansive sand unit that's kind of pinching out as you move to the right in that image. And so it's giving you a sense of how thick this unit is, how laterally expansive it is, and you could use this kind of information to steer potential drilling efforts. But at this stage, we're generally talking about these red and blue images. So it's not directly geological at this point. It's still in terms of these electrical resistivity properties. And unless you're a geophysicist, you don't necessarily care what the electrical properties are of the subsurface. You're more interested in knowing the identity of these hydrogeological units. You care about things like water content, permeability, more physical parameters linked to the groundwater system. If we click to the next slide. So to convert these images of electrical properties to more useful interpretations of hydrogeological units, we can rely upon decades and decades of EM literature and EM experiences that have been done in the field, where we can kind of take advantage of the fact that different hydrogeological units can often be differentiated based on their electrical property. So with a little bit of background information, so for example, in Denmark, we're commonly working with glacial sediments, which is in the center of this image here. It gives us some insights that when we see very resistant materials or blue in this image, we can often affiliate them with sands or gravels or good aquifer materials typically. And in the other end of the spectrum, when we see very conductive materials or red in this particular image, in the Danish glacial setting environment, we typically associate those with clays. So with a little bit of geological background, it's quite easy to map these electrical images into images of what are the likely identities of these hydrogeological units. And another feature that I'd like to point your attention to is at the bottom of this panel, at the very bottom left, you'll see that salt water is extremely conductive, or red in this particular case. And as we move to the right in that image, you'll see that fresh water corresponds to higher resistivities. So it's a very strong electrical contrast between the two. And so it's a very good imaging target for these kinds of technologies, where it's very easy to differentiate between a salty water and a fresh water, for example. And if we click to the next slide. And so returning to this image that we've just previously seen, this is what we're doing when we're assigning these labels to these types of images. We know that in this context, reds are typically corresponding to sands, and blues are typically corresponding to clays in this case. And so you can get a quite robust interpretation with just a little bit of geological background. And this step is one of the most challenging that we'll have to confront when you move into data poor environment. Because when you don't really have a good sense of what the background geological setting is, this is a step that can become quite difficult and introduce a lot of uncertainty into your interpretation. And so it's a situation where these interpretations of these images don't necessarily have to be static. So if you're producing an image and recommending a borehole site, if that borehole is then drilled, it gives you a chance to actually observe what these units are at depth and improve your interpretation of these types of images. So in the context of a multiple drilling campaign, these things should be updating as you're going and kind of improving your interpretation to reflect available data. But we're not only restricted to viewing these kind of 2D representations of these 3D volumes. In many cases, it's extremely powerful to be able to maintain these images in 3D. If we click over to the next slide. This is one such example. This isn't a groundwater, or at least a Tanzanian groundwater example anyway. So this is an image that was taken of a glacier that's in Antarctica. So in purples, we have extremely resistant glacier ice. And of interest was whether or not there was a potentially brine aquifer system at the base of this glacier. And so one of the things you can do in these images is you can blank or mask voxels that correspond to geological units that you're not necessarily interested in. So in this lower image here, what we've done is isolated only the extent of that lower briny aquifer system. So a really powerful visual tool in order to build out your conceptual model of how expansive these different geological systems can be. If we click to the next slide. So that was just a brief discussion on the typical data products that we're producing with this Ttem system and how you can link electrical properties to their geological identities. And now we'll give a few examples of how we can use this in practice to try and improve drilling efforts in data poor regions. So the first examples that I'll talk about come from a survey that was done in Tanzania in October of last year. And so this was done in partnership with Water Mission Tanzania, and the system was taken to Tanzania, and 7 different communities, or 5 host communities and 2 refugee camps were surveyed over a 1-month period. And I'll give you a couple of examples from first a refugee camp and then a host community. If we click over to the next slide. So the 2 refugee camps that we worked in are known as Niragusu and Nduta camps. So Niragusu is the image on the left, just the satellite image shown here. It's home to about 170,000 refugees, mostly Burundians. The image on the right corresponds to Nduta camp, which is a smaller camp that's home to about 74,000 Burundian refugees as well. And both of these camps have some water infrastructure that's present in the camp, certainly. They're not entirely dependent on surface water. There is some groundwater exploitation that's being done in these camps, but there's still a heavy reliance on local surface water systems, in particular rivers that are running nearby the camps. And so there's a desire to increase the camp's dependence on groundwater to get them off of these surface water sources, both because they represent a potential contaminant risk, but also to lessen their impact on the rivers, which are important water sources for local Tanzanian villages further downstream. And if we click to the next slide, but it's not always the case that these communities have quite developed water infrastructure in place, in particular the local host communities in the Tanzanian villages. In certain cases, the towns are fortunate to have some kind of infrastructure in place. So a number of the communities we worked in have productive boreholes and holding tanks and even distribution networks that have multiple access points throughout the community. But it's not the case in all of the. So Kitagata, this particular example that I'm showing here, it's a Tanzanian community that's to about 5,000 people. They depend exclusively on water sources that are coming from either shallow hand dug wells. So an example shown here on the left image of a shallow hand dug well, or local spring. And we're seeing two images on the right-hand side here. And so these are obviously not ideal solutions for a town of this size. There's not a lot of protection, so there's contaminant risks associated with these types of water sources. But another important factor to take into consideration is the distance of these collection points from where most of the people are actually living. A sizable portion of this community spends a significant amount of its day just collecting water. People are walking over a kilometer each direction in order to get this water. And at the end point, you're picking 50, 60 liters of water and then having to carry 40, 50 kilos back over a kilometer to your home. So anything you can do to even potentially find a water source that's more conveniently located can really go a long way towards alleviating the daily burden. If we click over to the next slide. Yeah, so now I'll talk about some of the results from this survey that was done in Kitagata. So one of the first things we do when we're going to these communities is we're speaking with the locals and trying to gain as much metadata about the local groundwater systems as possible. And in many cases, this is limited to simply having them drive us around and show us all of the local water collection points. So having knowledge of where springs are present or the water table in these shallow hand dug wells is still extremely valuable information when we're trying to complement and build out our interpretations of what these groundwater systems are, so that the EM data doesn't necessarily have to stand on its own. It can be supported by other supplementary data types. If we click forward, so this is an example of Pardeep, who spoke earlier, actually driving the system through one of the communities, just to give you a sense of what data collection actually looks like. In Tanzania, we were somewhat limited in terms of data collection speeds. If you were watching earlier, there was a video of the Ttem system being driven in a field in Denmark where it was driving much faster than this. When you're operating in close vicinity to these structures and with crowds, and in particular on these hard, smoothed surfaces that were present throughout much of the area, you're often restricted to about walking speed. So data collection was somewhat reduced compared to normal production rates elsewhere in the world. But one of the surprising advantages, if we click forward, was that we were able to produce very high quality data in the interior of the community, which was something that we weren't so certain that we'd be able to do pre-survey, because many of these homes have tin roofs or there's metal bodies around that can often cause distortion in the EM signals, but it's not something that in these cases we saw had a significant effect on the data. As long as we were operating the system in the non-electrified regions of the communities, then it was okay to produce high quality results, as shown by these green areas here, which gives us some indication of the quality of the data that we're producing. If we click forward to the next slide. So beyond locating springs and wells, we try to amass all other supplementary data, and really that was all that was available in these areas was digital elevation models, or even global digital elevation models. So this is a 30-meter pixel digital elevation model, but what you can see is it just so happens that many of these communities tend to live at local highs in the topography. In large part, I'm guessing because they have less flooding in the wet season if you live at the local highs. But one interesting thing you can get from this image already is that all of those springs, or those orange dots, they seem to pop out at around the same elevation. So there's already some indication that there may be an unconfined aquifer system that's popping out at those altitudes. To further kind of build out this interpretation, we performed Ttem measurements in the area. If we click forward to the next slide. Here's some examples of the results that the Ttem's producing. So in that upper image that's labeled red profile, that corresponds spatially to the location of the red line in the leftmost map. And what we're seeing here is you move from the left to the right in that image. You're moving from an area of largely blue or sort of very conductive materials, so a clay-rich setting. And as you gain in altitude, as you're moving into town, we can see that this gain in altitude corresponds to an increasing thickness of this very resistive unit, which is being interpreted as the laterite. And the location at which this blue unit is intercepting the ground surface happens to coincide with the location of those springs. So it's starting to build out this interpretation that on the top of this blue unit, you have an unconfined aquifer system that when the elevation's dropping is intercepting the surface and producing these kinds of springs. If we look at the lower image labeled blue profile, which runs through the center of the town, you can see that in the center of the town, you have this thick purple layer, this thick resistive cover that sits always atop this rather continuous blue layer at the base. And so this is suggesting that if there's an unconfined aquifer system that's pinching out on the exterior of the town in these lower elevations, it's likely also present in the center of the town. And so this is giving you some evidence that if you were to drill a borehole to, say, in this case, 45 or 50 meters, it's very likely that you're going to intercept an unconfined aquifer system that's sourcing the springs that the town is already reliant on at the edge of the town or at the edge of the community. But just one example of how these Ttem surveys can kind of guide potential future drilling efforts. If we click forward. So here is an example from one of the refugee camps. So this is from Nyarugusu, which is home to 170,000 Burundian and Congolese refugees. So our surveys in Nyarugusu focused predominantly on the northern extent of the camp, and this was because of a recommendation from the Norwegian Refugee Council that operate the camp, that if there was ever a wave of future expansion, they would push the camp to the north. And so there was an interest to see if the geological setting in the northern region of the camp was consistent with a particularly productive borehole that they had drilled in the northwest corner of the existing camp. So there's a cluster of 3 orange dots forming a triangle, and then a single dot that stands above that is that location corresponds to an extremely productive borehole that was producing over 100 cubic meters per hour. And Water Mission has built quite an impressive infrastructure to support this borehole. There's a significant solar array, there's water treatment facilities, and then a distribution network that supplies much of the northern extent of the camp. And so there was a lot of questions as to whether the system that's encountered at that location could also potentially be intercepted in the northern regions of the camp. And so if we click forward in the slides, that's what we're seeing in these images here. So in that upper profile labeled red profile, in the left-hand side of that image, we're starting at a location that's right next to the very productive borehole. And then as we move to the right in that image, we're moving further to the north of the camp. And the first thing that we immediately see is the lateral consistency in this image. So you have this thick blue layer near the surface that extends the full length of the survey. And underneath this is a more resistive unit. And at depth on the left-hand side of this image, a very significant water strike was found at about 100 meters depth. And so when we look at these types of images, we're kind of using them in a way to extrapolate from a known point where we have a productive borehole to other regions. So when you move to the bottom profile again, which is even further to the north of the camp, you see this same kind of layered structure, blues on the top, reds underneath. We click to the next slide. Again, here we're just looking at 2 more images, now further to the east, but still in the north of the camp. It's this same structure. So you're seeing consistency in this layering, and layering that's consistent with a known location of a very productive borehole. If you begin to stitch all of these results together, if we click to the next slide, you can begin to build out this kind of comprehensive 3D visualization of the entire system. So the region in blue that's now at the kind of bottom of that panel, this corresponds to the northern region of the community, or the northern portion of the refugee camp. And the thing to note is the lateral consistency across this. So it's suggesting that if you were to drill a future borehole in this area, it's very likely that you'd encounter the same system that's been encountered at that very productive borehole. So it gives you a lot of confidence that if you were to employ a similar drilling strategy as to that you've used previously, there's a good chance that you'll result in a productive borehole in this case. But to produce these kinds of images, one of the things that we're really trying to emphasize in this project is to make a data flow that's as accessible to non-expert end users as possible. If we click over to the next slide. So a big effort in this push has been to automate as much of the workflow as possible, trying to strip off a lot of the highly technical experience required steps in these data workflows. So now we have an acquisition system where a user can be trained in some kind of low-level operation of the system, not really having to understand, say, the mathematics behind the processing or the mathematics behind this imaging, but instead just kind of being taught in how to produce quality data, check to ensure that data looks okay, and then already be producing images of the electrical properties. Where at the end of a survey, data is already written into a format that can be loaded into software to directly produce those 3D images that we just saw. If we click forward. Yeah, and so this was just a couple of examples from the Tanzanian survey. So in February of this year, we had a follow-up campaign that was conducted in South Africa, where we conducted surveys in a number of different communities all across South Africa in an attempt to target a number of different geologies, particularly in the Cape Fold Belt in southern South Africa, where we were working in hard rock environments and these fractured rock settings, which is quite a unique or new setting for the Ttem system anyway. But you can even see that in the second campaign, the production rates were significantly higher than in Tanzania. In Tanzania, daily production was averaging maybe 15 to 20 kilometers of data collection per day, whereas in South Africa, when we got to much more open terrain, where you didn't necessarily have the restrictions of the structure or the large crowds or the brushy terrain, you can collect data at much higher rates. I think our highest data production rates in South Africa approached 80 kilometers in a single day, so a lot of data coverage is possible. And then unfortunately, with COVID, some of the drilling campaigns have been postponed. We had hoped to be able to have a few more success stories to share with you in these sessions, but we do have a few instances of success, if we click over to the next slide. So the first was in a small community in South Africa called Sediba. So there was interest in drilling a borehole in this small, somewhat restricted area. The campaign was somewhat limited to a fixed small region that the community had rights to drill in. But we did a survey within this area, and then there was an identification of a kind of dominant three-layer structure where there was a conductive unit at the surface, underlain by this big, thick red unit, which is interpreted to be a sandstone. And then at the base, where we have a lower conductivity, I think it was interpreted to be some kind of a shale at depth. And of interest in this case was the bedding planes between these units, because it's likely to correspond to increased fracture density. And if you can find at depth beneath the water table levels, these highly fractured bedding planes, they tend to be very productive aquifers in these settings. And so a well was drilled at about midway of the center of this profile. If we click over to the next slide. And then at the depth where the imaging from the TEM predicted an interface between these sands and this lower conductive unit, or the sandstones in this lower conductive unit, there was a significant water strike. And here we're watching a video of the blow yield tests, where it was found to be quite a productive borehole for the area and capable of producing about 75 cubic meters per hour. So a pretty good success story for this community Sediba. And then there's also been drilling efforts done in a follow-up campaign in another town called Langsburg, and we've got plans to do drilling in a number of different other sites as well. Hopefully the next time you hear about these results, we'll have more success stories. If we click forward. Yeah, and just to summarize, I really believe that these types of imaging technologies should become a staple part of the pre-drilling workflows, because effectively it's just risk mitigation. If you have these expensive wells that need to be installed, you could potentially elevate the likelihood of drilling a successful well by doing these kind of rapid, cost-efficient pre-drilling campaigns. I think especially when you're talking about doing large-scale drilling campaigns, committing a small pool of funds from the project to a regional geophysical survey goes a long way towards probably increasing the final outcome of the project. Ultimately, if you can raise the success rates of those boreholes, at the end of the day, it's probably going to deliver more successful boreholes. And then I think at this point, we're happy to open it up to any questions.
Does anybody have any questions? You feel free to talk. We're not that many people, or type it in the chat, then I will read it out. Lawrence is typing. She asks, how does this methodology fare compared with traditional methods?
Yeah, I think at its core, it relies on the same physical process and the same physics as other traditional methodologies, in particular TEM, which is kind of a workhorse technology in near-surface geophysics for many years now. What makes the Ttem so special is that it fills kind of an unmet need previously. So you had ground-based systems that were man-deployed systems, were relatively cheap and easy to deploy in the field, but lacked this ability to give you large-scale spatial coverage. To solve that, people developed airborne systems where they could be picked up and flown with helicopters or airplanes, and those systems are stand at the king of the pile or the top of the heap in terms of spatial coverage, but they come with other logistical and financial limitations just because you're involving aircraft and doing these very large-scale surveys. So there was kind of this middle ground for a rapidly deployed regional system that could focus exclusively on this top 100-meter interval or so. And that's where Ttem has really, I think, kind of struck a chord and bridged the gap that existed between these other traditional techniques.
Thank you. Carrie wants to ask, are there any models to predict the effect on the aquifer if water is withdrawn at various levels of use?
Yeah, that's a great question. And this kind of monitoring aspect is something that is very much an ongoing research topic within our group and within other groups as well. You can think of these kind of single mapping campaigns more reflective of a snapshot of the system in time. You're doing a mapping campaign that's conducted, say, in a 1-week interval, and it's giving you a sense of what that system looks like at that time. You can take that result and put it into hydrological models and then use that to predict the behavior of the system due to some change in external stimuli, increased precipitation rates, droughts, these kinds of things. But the image itself is representative of just that snapshot in time. One way to get around this would be to do repeated mapping campaigns where you could see changes in the same location over long durations of time. That could give you some insights into these kinds of questions. But there's still, I think, a complementary set of technologies that could come in and do this long-term time-lapse monitoring, really complement the lack of temporal resolution these mapping systems have.
Then Mohammed is asking, how can this methodology be used to map multi-layer aquifers for national hydrogeological surveys?
Yeah, that's a great question. And so when we're producing these images, we're imaging depth variations in the system. So if you have multiple aquifer systems that are present, as long as it's above the depth to which we can produce usable data, then we'll resolve them typically. What we find is that you have very good resolution at shallow, and as you go deeper, your resolution is poorer, but there's no inherent reason why you shouldn't be able to differentiate between different aquifers in a layered setting, for example.
Chris Bryan is typing. Anybody else has questions? You can speak out. Oh, it says, Amit asks, can it be used in sandy areas?
Certainly. It's commonly employed in these kinds of sand-rich, sand aquifer, gravel aquifer settings. Much of Denmark is that way. And that was where the technology was kind of built. But it's certainly not a setting that the system wouldn't have been used in before.
Hey, this is Chris Bryan. I think I'll just say my question versus type it all out, which is the idea for this software that you've developed to make it simpler and the workflow that's been developed. Is it to commercialize it to then for national hydrogeologists to use, or is the idea that this would be something that can be deployed that maybe one organization uses and then deploys themselves, or just a few organizations deploy as almost like a research level project?
No, the plans are to make it ultimately commercially available, where these kinds of simplified software and workflows would ideally expand the customer base to non-geophysicists, where the plan is to build these types of automated workflows where you don't necessarily need to have the experience with all the nuts and the bolts that go into it in the moment, but still be able to produce a reliable outcome at the end of the day. And even if that outcome isn't 100% of what a postdoc in geophysics would get you, if it's 80 or 90% of that, hopefully it can still get you to that decision point where you can have a reliable image and still make a good interpretation.
Okay, thank you.
Mohammed asks, is the Ministry of Water in Tanzania aware of this work?
Yeah, we actually, we had Ministry of Water representatives with us in the field throughout the campaign. So we worked with a local hydrogeologist from the Kasulu offices, and also a hydrogeologist from the Dodoma offices as well. We had 2 representatives.
Okay. Chris, I can see you typing. Do you have another question?
No, sorry, I think it's just perpetually showing me typing now.
Okay. All right. Any other questions? What accuracy tolerance does the system have? Asks Amit.
Yeah, that's a great question. So your ability to say differentiate between different geological units is kind of dependent on the fact that there needs to be an electrical contrast between the two. So if you had two contrasting or two different geological units with the same electrical properties, as far as the TEM system would be concerned, it would image a single unit. In terms of accuracy for resolving electrical resistivity values, it's more difficult to resolve kind of absolute values in this very resistive limit, whereas you can get higher resolution in the more conductive limit. But generally, to get you most of the way there, it's really just kind of trying to map structures with these things, and it's not necessarily as important to have completely absolute values for these things. They kind of just guide your interpretation when you're trying to identify these different units.
Okay. Sarah Heyman asks, similar to Chris's question, you mentioned that the surveying and data analysis could be managed by technicians without an understanding of complex mathematical modeling. Has there been any field testing thus far in a participatory manner or involving such type of people using the software?
Not yet. So the development of these kind of live inversions and writing data in formats that can be loaded into these kind of easy to use visualization softwares is very much ongoing and new research within our group. It's currently at a stage where it's commonplace for us to have, say, master students be trained in how to operate the system and then be able to use these kinds of workflows themselves with some kind of supervision post. But this is something that we're very interested in kind of scaling and kind of pushing these new automated workflows into the hands of more people and stress testing them, really, making sure that they're as robust as possible at the end of the day.
All right. Any other questions?
Anna, is it okay? I just have a comment regarding the idea of measuring over time or what do you call it? Monitoring over time. It's more due to saying that when we talk about those very remote communities, and even when you talk about the forgotten refugee camps where you have a lot of people, it's still into a relatively big area. And normally you say when you talk about sub-Sahara, you don't have an environmental water scarcity, but it's more an economic water scarcity you have down there. So you simply don't have access to water, and that's because it's too expensive to drill for water. But of course, it is very important when we start to drill and when we start to take the groundwater out for drinking water purposes or even irrigation, that you're monitoring your groundwater level in the future as well, to make sure that you also do it in a sustainable way.
Sorry. Okay. I don't see any other questions. If this is the case, I'd like to thank you all for your attention, and we'll post this video also on the YouTube channel of the World Water Week and on the Foundation's website. And you can also check back on the session pages on World Water Week to find them. Thank you for your attention and have a nice evening. Oh, Chris is typing. Oh, that's lovely to see. Thank you very much. Bye-bye.